My name is Vartika Verma, and today I'll be presenting my research work on the analysis of piezoresistive silicon, and primarily in the use of flexible tactile sensors. So piezoresistive silicon can be used in a lot of different applications, starting from healthcare, consumer electronics, advanced robotics, as well as in biomedical applications. But no matter what area we're talking about, the basic way we characterize sensors are in terms of flexibility, sensitivity, how much pressure they're able to measure, as well as how fast the sensors respond. And while all these four factors are important while we talk about the performance of a sensor, there are two more things which are often left ignored. The first one being the ease of system integration, and the second one being how easy it is to manufacture them in a larger scale. And the reason why I say that these two factors are important is because sensors don't exist in isolation. We always need some sort of a readout circuitry which you can amplify the signal and convert it into something that can be easily processed. And oftentimes, if the sensor and the readout circuitry are far apart, they are more susceptible to noise, and that would ultimately determine the resolution of the entire system. And then secondly, the manufacturing would obviously affect the cost, and that would determine how accessible this sensor or the entire system is to the general public. So the motivation behind my research was to generate a sensor system which not only works with the top four factors, but also takes into account the integration as well as the cost aspect. And in order to start, what we decided was to use silicon as the primary sensing element. So silicon itself is a piezoresistive material, which means when you bend it, it generates some stress and it will change its internal resistivity automatically. So this formula by Fruet tells how the resistance or resistivity of silicon would change based on the applied stress. And furthermore, because silicon is an isotropic crystalline material, that means that depending upon the angle that your resistor sensor makes with respect to your reference, and the angle that your stress makes with respect to your reference, the behavior of the change in resistivity would be different. So what that means is that silicon, due to its inherent behavior, not only can tell us how much is the magnitude of the applied stress, but it can also give us a directional sensitivity based on how much is the angle of the applied stress with respect to the reference. And so what we decided was, given the choice between the type of material that you would use, we can see that the N-type silicon would be more sensitive if you want to measure stresses in the normal and orthogonal direction, whereas a P-type silicon would be much more sensitive if you want to measure something in the shear direction. So again, there is a lot of customization options available within silicon itself, depending upon what your application target is. And similarly, this is how the sensitivity would depend based on how your doping concentration is. So what we notice here is that for lower doping concentrations, the silicon sensitivity would be pretty independent of the fabrication mismatches, but it would be pretty sensitive to the temperature. Whereas when we go to higher dopant concentrations, the sensitivity would decrease a little, but it would be more or less temperature independent. So again, thinking about how you would want to design your readout circuitry, you could choose what type of doping you would want for your silicon. So given this background, we decided to make our silicon chip by placing 64 identical sensor units on the bottom left quadrant. And each black dot that you see here are two identical resistors. So one of them is oriented in the X direction and the other one is oriented in the Y direction. And similarly, we placed two sets of 16 resistors each, where each blue dot represents two resistors, one oriented in 45-degree direction and then another one in 135 degree. And just for the sake of this experiment, we chose the most basic type of resistors that any fabrication house could offer, which is an N-type diffusion resistor. So if I put in the angles that these resistors make with respect to the crystalline reference like we showed earlier, we can basically come up with these four equations, which tell us how the resistance of each of this element would vary depending upon the stress applied in the X direction and the stress applied in the Y direction. So this is how a fabricated silicon chip looked like, and this is roughly where our sensors would be located. So after fabrication, the next step for us was to thin the silicon chip so that it could be more flexible, and then second would be to embed it in a flexible substrate so that it could mimic an electronic skin. Now the thing about thinning is that the thinner your silicon chip is, it would be more flexible. That means it will be able to experience higher stresses. But then the cons of such a system is that very thin chips become very difficult to handle, and then obviously the process becomes more costly. So our aim here was to think about more intermediate thickness values, which could also be fabricated easily, but can also resist breaking while handling. So this is how we decided to embed it in a flexible foil. We used a process known as flip chip bonding. So wherein we have a flexible foil, which in our case was a polyamide foil of 50 micrometers thickness. We deposited some copper trace lines for our electrical connections. We deposited some AC adhesive, which has these floating conducting nickel balls on top, and then we flipped our chip and placed it on top. So whenever we see these conducting balls creating a connection between the pad of the chip and the copper trace lines at the bottom, we have well-established electrical connections. And then this entire system still remains pretty flexible because the entire thickness is still within 200 micrometers. Now, given the mechanics of such a system, the neutral axis would lie somewhere along the silicon chip. And because our silicon chip is flipped, all our sensors would lie below the neutral axis. So this is how our foil looks like, and this is where our silicon chip is. You can see these fine lines which show how we back grinded our silicon chip to reach our desired thickness. And this is how our bending setup looked like. So we used different cylinders of different radii and wrapped our foil around it to apply some external stress. And primarily for our experiment, we applied stress in the X direction. Now, in order to look at the results, the very first thing we did was we simulated the same model using COMSOL. And then we looked how the stress response behaves like. And because all our sensors are within the silicon chip, so we are more interested in the stress response here. So this is the slice of the silicon chip where our sensors would be located. And from the COMSOL, first thing we realize is the maximum stress is applied around the center. And as we move along the bending direction, the stress magnitude decreases. And the second thing we notice here is the value. So it is negative 12 megapascals, which shows that the stress that we should expect would be a compressive type of stress. And if you compare it to our experimentally measured values, this is where our sensors are located, those 64 normal sensors that I showed you. And not only do the measured values match perfectly well with the simulated values, but it also shows us the exact same gradient, which means that sensors which are closer to the center of the chip see a higher magnitude, and then as we move away from the chip towards the edges, the stress decreases. And then if we look at individual resistors, we see that the resistors which are oriented in the stress direction see a much higher change in resistance as compared to the Y directional resistors. So that means we could not only tell the magnitude of the stress, we could also tell the type of stress, whether it was compressive or tensile, and also the direction of stress in which we applied our bending. Similarly, another thing we notice is that for the same amount of bending, a thinner chip would see a much more higher stress as compared to a thicker chip. So here, the change in x-directional resistors was almost twice as compared to the x-directional resistors for a thicker chip. So if we look at this chip, remember now our chip is flipped, and we focus on this section, these are the results that we see. Not only do our normal resistors show us the similar behavior, but individually if we use the 45 and 135 resistors, they also give us the same gradient. Furthermore, when we use a tighter bending, the amount of stress that we sense also increases. And if we compare this with a thinner chip, we see that the gradient response remains more or less the same, but the amount of stress almost doubles. And it's the same for a tighter bend here. Another interesting thing that we notice is that when we have thinner chips, the gradient becomes more uniform. That means throughout the internal chip, the same stress value would be seen. And last but not the least, this is the temperature response for our resistors. So as you can see, it remains pretty linear no matter what thickness you use, no matter what bending you use, which also makes the corresponding readout circuitry design very easy. So depending upon how would you like to compensate for it, this becomes a very simple approach. And so these are the final conclusions. If we use silicon as a primary sensing material, first of all, we can control the flexibility and sensitivity by choosing what thickness you want. We can detect the magnitude, the direction, as well as the type of stress. Silicon has a very high linear pressure range, so you can basically measure up to plus minus 200 megapascals. And again, because we are using silicon, we have a higher mobility and a higher response time. And more importantly, because all our sensors are within the same chip, you can have the readout circuitry as well as the sensors at the same time. And that means the integration is easier and everything can be fabricated through the well-established CMOS process. So it's a pretty simple way to make very basic and effective tactile sensors. That's it. If you have any questions, I'll see you.
Yes, Thanks.